Swayam Prabha. Digital India. Educated India.
Hello, welcome to the last lecture of week 4. This is the last topic on bidirectional bending of a beam. So, let us, in the last lecture, we have derived the expression for the deflection u and v in the x and y z direction and in terms of the applied moment and the sectional property. So, we have found out that you can write mx as minus EIXY u double dash where u and v are the deflection of the beam in x and y directions. So, if I have an arbitrary beam section, if as we have been using x and y are the cross sectional coordinate axis, then u is the displacement in x direction and v is the displacement in y direction. Now, from this two expression we can actually write, instead of writing mx and my in terms of u double dash and v double dash, we can write u double dash as so, I can just derive this two equation from the above equations. Now, once I get this, then I can obtain u and v in terms of the applied moment and the sectional property of the cross section, and thereby find out the deflection of the beam in x and y direction. So, let us just do a small example and see how we can solve the problem. So, let us take this example. So, let us consider a cantilever beam Let us consider a cantilever beam of length L. So, this is the length is L. So, let me also draw the x, y and z axis. And if we take any arbitrary cross section of the beam, so let us take an arbitrary cross section AA, and so let us say that this is the cross section AA. Now, let us say that z is equal to 0 here and z is equal to L here. Now, let us consider that a tip load W is being applied to the cantilever beam. So, I apply a tip concentrated load W on the cantilever beam, and if I ask the question that find the tip deflection of the beam. So, let us find out the tip deflection of the beam. So, how are we going to solve the problem? So, the first step that we have to take is that let me call this as equation 1 and equation 2. So, we know for this applied force W, I will have mx as W L minus Z, whereas my is going to be equal to 0. So, if this is the case, then I can use equation 1 So, we can use equation 1. So, for a tip load in the y direction, we can we know that the moment in x direction will be W L minus Z and moment in y direction is going to be 0. Now, if we use equation 1 for this problem, then we get u double dash is going to be equal to, so my is equal, so that is equal to mx into Ixy minus my into Ixx by Ixx Now, in this expression my my is equal to 0. So, therefore, this expression boils down to mx Ixy by E Now, in this expression mx is equal to W L minus Z. So, this expression therefore can be written as W L minus Z into into Ixy Now, if this is the condition, then we can further write that u double dash is basically d2u by dz square, which can be written as W L minus Z into Ixy by So, this would be the condition. Now, in order to find out u, I have to implement the boundary conditions. So, by imposing the boundary condition. So, or let us first integrate and then we will impose the boundary condition. Let us just integrate this and then we will get from this that u g u z is going to be w into I x y into, if we integrate this, we will get L z square by 2 minus z cube by 6 plus C1z plus C2. Let me just write it here. So, what I am going to do is I am going to take an integral of this, and this therefore is going to be u z. If I take integral of that, I will have I x y okay, and integral of that is going to give me L z square by 2 minus z cube by 6 plus C1z plus C2, where C1 and C2 are the constants that we have to deal with. So, C1 and C2 will be found out from the boundary conditions. So, now let us see how are we going to solve it. So, therefore, u z, let me just rewrite this, is w I x y into L z square by 2 minus z cube by 6 plus C1z plus C2. So, this is the expression that I get. So, let me call it as equation 3. Now, let us impose the boundary conditions. So, boundary conditions for the cantilever beam is given that u0 is going to be 0 because it is fixed at z equals to 0, and u dash 0 is also going to be 0. So, at z equals to 0. So, these two are going to be 0. So, if we implement this boundary condition here, then we will find out that both C1 and C2 is going to be 0. Therefore, u z turns out to be w into right. So, this is what we get, the expression for u. Now, if we apply if we try to find out the tip displacement in x direction, we have to just find u z at z equals to L. So, that is going to be w I x y by E I x x minus ixy square into L cube by 2 minus L cube by 6, which is going to be W L cube ixy by, so it is going to be 3 So this is how this is the expression for U tip. Now similarly, we will write down the expression for V dash. So V double dash, so from equation 2, we get V double dash is going to be W minus W. So we have the expression for V double dash. V double dash here is this. So my goes to 0. So we have V double dash as minus mx. So let me write down the expression for V double dash. So expression for V double dash is minus mx into Iyy So if mx we know, so if I just substitute the value, it is L minus z Iyy by E Ixx Iyy minus Ixy square. So we have to proceed with the same approach that we did. So d2v by dz square is therefore given as minus w into L minus z. So if we integrate this, we will obtain Vz as minus W into Lz square by 2 minus z cube by 6 plus a1z plus a2, where a1 and a2 are the boundary conditions. So now the boundary conditions for the cantilever beam for V are V0 is equal to 0 and V dash 0 equals to 0. So this two conditions implies that A1 is going to be equal to A2, which is going to be 0. Therefore, we can say that Vz is nothing but minus W Iyy So therefore, the tip displacement in y direction is given as V z equals to L, and that is going to be minus W L cube Iyy by So these are the two expressions. So this can actually be written as V tip. So these are the two expressions that I get. So, I get u tip, that is the tip displacement in x direction, and I get v tip, which is the tip displacement in y direction. Now, in order to find out the total displacement or deflection at the tip, we need to take the resultant of these two forces, these two displacements, and therefore, we can see that the resultant tip displacement which we can say that which can say delta is going to be u tip whole square plus v tip whole square, because u and v are the displacement in x and y direction, and therefore, they are perpendicular to each other, and the resultant tip displacement is going to be the square the resultant of these two. Now, once we have got this tip displacement, we also need to find out what would be the direction of the resultant displacement. So, the resultant the angle that this resultant displacement is going to make is given as alpha, is given as theta maybe. Theta can actually be written as tan inverse of u tip by v tip, because u tip and v tip are in the perpendicular direction. So, we by using this equation we can find out the resultant displacement, and by using this equation we can find out the angle of this resultant displacement with respect to the x axis. So, this equations that I have derived has been derived for a cross section of arbitrary shape. Now, but the moment was applied in only about x axis, and the moment about the y axis was 0. Now, for cases where there would be moment both along x axis and as well as y axis. So, let me draw such case. So, if I have a cantilever beam, say I have a cantilever beam or a simply supported beam, does not matter, and if the loads are like this, if I apply a force W in this direction or W x in this direction, and if I apply a force which is in W y in this direction. So, this is going to produce a moment m y, and this as usual is producing a moment x. Then in the expression we have to use non-zero value for both m x and m y. The calculation will become rigorous, would be much more complicated, but it's always a doable problem. So, even if we have both m x and m y, we can easily solve the problem by using the same procedure that we have discussed. In many cases, in addition to this, the tip displacement will also depend on the boundary conditions of the beam. We have discussed we have derived the example or solved the example for a cantilever beam. In place of cantilever, if it is simply supported or if it is a fixed beam, the boundary conditions are going to change, and accordingly we would need to solve for the displacement. The constant C1 and C2 as well as A1 and A2 will depend on the boundary condition, which will change the expression for u and v and thereby change the expression for u tip and v tip and the resultant displacement. Similarly, in aircraft structure we very often experience symmetric cross section, in which case Ixy is going to be 0 and therefore the solution, the equations for or expression for the displacement will become even more simpler, because Ixy is going to go to 0 and those examples would be solved much easily as compared to the complex example that we have solved in this lecture. So, with this lecture the module on bidirectional bending of thin wall structure is complete, or the week 4 is complete. In the next week, that is week 5, we will discuss about the shear stress in a thin wall beam cross section due to applied shear forces. Thank you.